Hi. So this is an additional video. I didn't originally intend to record this, but I thought I owe you this about what is the meaning of S and its relation to convolution. They are not related, but I want to relate them together. So let's start by this example. This is example 824 from the textbook. I'm not going to solve it again, but it's a double step function with positive and negative values. And follow the textbook, you'll end up with Laplace transform of this function g of t to be equal s. So this lecture is about what this means, what are its implications, and how it relates to the concept of convolution that we will talk about. So let's first talk about what is S. What does a Laplace transform of a function equaling S, well, what does that mean? There is one of the properties of Laplace transform. If you recall, if you have a function f with Laplace transform becoming f of s, the Laplace transform of f dot is s f of s, right? This is from the properties in one of the tables in the textbook. So that is what we have. I'm just going to flip the two sides of the equation and put it this way. S f of s equals Laplace of f dot. So usually we write this first and then Laplace of f dot equals f of s. I started the other way around. So what does this mean? It means if we have the Laplace transform of f and we multiply it by s, we are essentially taking derivative of the function. So s, you can think of it as an operator that can be used to take derivative of a function. If you will see it soon in Simulink, if you want to take derivative, I think the symbol of that block is s, if I recall correctly. I'm not too sure, but it used to be. So s, if you have a function in the Laplace domain, you multiply it by s, you take the derivative of that function. And this is precisely what this g of t is doing here. Well, okay, let me, this is not correct. Limit. No, this is incorrect. Why did I write this? This is limit as a goes to 0. That part is missing. As a goes to 0, the Laplace transform of this function as a becomes 0 is s. That very critical piece of information was missing originally. So imagine I have this function, and I multiply it by a function f of t, any arbitrary function. So I have f of t, could be anything. And I'm multiplying f by g of t. And it is g of t in its limit form is this and that. They are very tiny pulses. If I multiply f by that g of t, and then integrate it as g, the width of g, is getting closer and closer to 0. Essentially what I'm doing is I'm taking f of t and some f of t plus dt. Because the first part is positive, the next one is negative. If I multiply it and then integrate it over time, the rest of it is 0. The only thing I have is this difference. And the difference is what we need to take the derivative of f of t at that time. So this, already you see the connections. If you have s multiplying by some Laplace transform of a function, we are taking derivative. Similarly, in a time domain, if we have such a function and multiply it by f of t in a time domain, what we are end up with is something that resembles a derivative. And the last bit is convolution. So essentially what we do, if we multiply this by function f and take integral, we calculate derivative of f at this time 0. What is missing is kind of sweeping all across time, and that is what convolution is. Convolution is a mathematical operator. It is written as f of t asterisk or star g of t. This is not product. This is a symbol for taking or applying the operator convolution to these two functions. And its definition is integral minus infinity to infinity f of t g of t minus tau. I think so. No. F of one of them should be which one? It should probably be tau minus t d tau. Let me pause a little, double check. I'll be back. Okay, I checked, it's correct. So that is convolution. So what we are doing, we are flipping g, that is just flipping it, and then sweeping across from minus infinity to infinity, and doing this operation, essentially getting, in this case of doing that, the result is going to be the derivative of f of t. And one interesting property of Laplace transform, convolution, is that if you take Laplace transform of f of t convoluted by, or convolution by, I don't know how to say it, Laplace transform of this is very beautifully written, can be written as f of s, g of s. The product of the two Laplace transform of individual functions. And going back, closing the loop, this one was s, f of s, and here we saw through all of that this is f dot. So that is kind of the relation between this function, definition of convolution, and meaning of s being a time derivative. So this function is not the only one that has Laplace transform of S. There are a lot different versions, but these and a family of all of the family of all those functions that look more or less the same, they are all called, they are a form of filter. So if you, for instance, work with Simulink and you want to take derivative of a function, one of the things in the derivative block that you put in is the order of filter. So for a while I was not sure what that means, but essentially you can think of this shape function as a filter that you're passing, sweeping through, or you pass your function f through it, through that filter. And the shape of this can be defined in a lot of different orders. I believe this is could be first order or zeroth order, I'm not too sure. It can be higher order terms that gives you more and more accuracy in calculating the derivative. Often you assume a step size, a finite value of a, like, I don't know, 1 millisecond, and use that to approximate the derivative of a function. So I thought this would be interesting to cover and show you, for one thing, what is convolution. For another thing, what is what does S means in relation to Laplace transform, and how we can use these kernels, what they are called, filter kernels, to calculate derivative of a function in practical situation. And maybe one last thing that is a bit simpler than that. Starting from here, we could also do this. It is also one of the properties of Laplace transform. One over S also means integral in Laplace world. So I leave you with that. And I just wanted to I want you to have this intuition about what these products mean and how we can use them in practice. You need this lecture for one of the assignments. So now you have it. All right. See you later.